we've seen a couple of examples already where where we've seen that this is going to be practical. The using rectangles, especially only a few rectangles, is not usually very accurate because a function is changing, but the value of a rectangle or the height of a rectangle doesn't change. So the trapezoids can kind of account for that change a little bit where the rectangles could not. We have the question, why would we use rectangles when we could use trapezoids to begin with? We're going to see in a minute, we're going to have formulas for LRAM, RRAM, and TAM, the trapezoid approximation method. The formulas for the rectangles are simpler. And it actually ends up that when we're only using a few rectangles or a few trapezoids, the trapezoids are more accurate. But if we're able to use infinitely many of them, they're all equally accurate. Okay, so when we start taking limits and using infinitely many rectangles, or at least approaching infinitely many, the rectangles work just as well, and the formulas are simpler. So, good question. That's why we would use rectangles. So, I just want to give you an idea of what the trapezoid method looks like. We've already looked at this a little bit. Feel free to take notes on this if you want, but you certainly don't need to. But let's say that we want to approximate the value of the integral of this function from a to b. Remember, using rectangles, we end up with something that looks like this, and I'm going to make this a fairly big one. And we can see here that there's a significant amount of error there when we use rectangles to find an area. So what we can do is start using trapezoids. And I'm going to break this up into some sub-intervals here. Let's just make it 4 somewhat equally spaced. I'll do my best to make them equal. We'll see here that when we have trapezoids, even though this is kind of an erratic function, the trapezoids are going to have much smaller errors. So even though they're not exactly right, we can see that it's closer to the function than the rectangles were. So the trapezoids, when we're doing an approximation by hand, they can be a lot more useful because we get a closer approximation with less effort. Okay. Now let's talk specifics here. I'm going to call this x sub 0, x1, x2, x3, and x4. Okay, so these x values, we're going to assume, even though I didn't do a great job of it, we'll assume that the differences between the x values are all the same. And what do we call that difference? The change in x, or delta x. All right, so I'm just going to mark that on one of them here. This distance for all of them we're going to call delta x. And we came up with a formula how we would compute delta x by finding the width of the entire interval from a to b, subtract b minus a, and then divide by the number. So divide by 4. Okay? So these trapezoids here are called right-angled trapezoids because they have right angles here. And to find the area of one of these trapezoids, what would we do? I'm going to label this function f of x. So let's say I want to find the area of just this trapezoid right here. How would we do that? Okay, so f of x naught, or x sub 0. So this right here, the f of x sub 0, that's this height right here, right? Okay, that's actually one of the bases of the trapezoid. Okay, the other base is f of x sub 1. And then what do we have to do to find the area? Okay, add those together and divide by 2. That's the average of the bases. And then we multiply that by the delta x, the height of that trapezoid, which the height is the way we would look at it as width. Okay, that's the area of just the first subinterval. Now, if we do that over and over and over again, 3 more times to be specific, we're going to have 3 more terms that look like this, right? let's think about what those are all going to have in common. I'm not going to show you all of them. I'm gonna write a sub 1 here. So that's the first area. What are they all going to have exactly the same? Okay, the delta x and the divided by 2. So when we're using the trapezoid approximation method, assuming that the subintervals have equal width, we can say that we can factor out that delta x divided by 2. Okay, that's going to be in each term. Now, what are they not going to have in common, but what are they all going to have? They're going to, the heights of those functions, right? So let's think about this. The first one is going to have f of x sub 0 plus f of x sub 1. What's the second one going to have? Okay, f of x sub 1 plus f of x sub 2. What about the third one? Okay, x sub 2 and x sub 3. And then how about the last one? 3 and 4. Okay, so what do you notice about x sub 1, x sub 2, and x sub 3? They appear twice each, right? So what we end up with then is the first and the last ones only appear once, but the middle ones, all the ones in between, so x sub 0 only appears once, but all the ones in between appear twice. I'm just going to put, well, I don't need the dots, I guess. Trying to be really neat here with this. Does it make sense, first of all, why we have the delta x divided by 2 out front? I just factored that out because that's what they have in common. Once we do that, all we're going to have is a bunch of f of x sub somethings added together. Does it make sense why we only have one f of x sub 0 and one f of x sub 4? And then we have 2 of each of the ones in between because those are doubled up. Okay, now, I want to show you something here. This is going to tie it back to the rectangles. What if I just did f of x sub 0 plus 1 of the x sub 1s, 1 of the x sub 2s, and 1 of the x sub 3s? What would that be? So if I just use one each of the middle ones and then the left one, what am I really doing? And I multiply that by delta x. That's the left rectangles, right? Okay, if I use one of each of the middle ones and the right endpoint and multiply it by delta x, what am I doing? The right rectangles. So if I add LRAM and RRAM together, I get this with the delta x out front. And then I divide by 2, and I'm finding the average of LRAM and RRAM. So the trapezoids are actually the average of the left rectangles and the right rectangles. Now, it's not always the case. If they're not equal subintervals, then it starts to get a little bit screwy. But if they're equal subintervals, that's always going to be the case. If you know LRAM and you know RRAM, average those together and you get the trapezoids.